Hello everyone, I am Pranjal Tiwari, MS22. Today our talk will be on cosmology, Big Bang and inflation. Is everyone comfortable with Hindi? No? Okay, fine, it's fine. So, how many MS24s are here? Everyone? Okay, who is teaching you physics? What have you taught till yet? He has taught special relativity. I mean, he has not taught special relativity. He has taught special relativity. And he has taught the that's fine. Have you taught anything about tensors? Moment of inertia tensor? Yeah, right. Okay, let's begin. You all know about Big Bang? Can anyone tell what the common picture of Big Bang is? Speak, speak.
Big Bang was sort of an explosion which created
Explosion that creates matter. It did not start as microwave because of the expansion. It has become microwave now. So when it started, it was higher frequency light. Okay, we will talk about what our current best model of cosmology and Big Bang is right now. You said Big Bang is commonly thought of as a singularity. Singularity does not actually exist in nature. It is just that our theories are not good enough for t equals to 0 starting of a universe. Hence, we call it as singularity. So, none of the singularities are physical. So, let's draw a timeline of our universe. So this is the t equals to 0 where we think the singularity is, but we know what happened after this moment pretty well. We do not know what happened at t equals to 0. We will have to build quantum gravity for that. So there is still time. We know what happened after that. We have our theories. We still don't know what happened. So our current theory is that universe was very small and very dense in the beginning, and then it expanded and gave rise to galaxies and whatnot. Okay, so we say that the Big Bang singularity was not a point in space, but a moment in time. It happened, the explosion, which we call the explosion, happened around t equals to 0. A little bit after that, we do not know what happened at t equals to 0. Okay. Okay. We say that our universe was very small. The part of our universe that we are talking about is the observable universe. We know that the speed of light is a constant c, some number around 3 into 10 to the power 8. Because of the finiteness of the speed of light, we cannot see the whole universe all the time. So if you are here, then anything within this radius from which the light had the time to reach you, you can only see that. Outside that, you don't know what's outside that. Okay. So the thing we call was very small was our observable universe. So our observable universe is a sphere like that, and there can be more universe outside this. We do not know if there is, but we say that our universe is infinite because we observe that our observable universe is almost flat. So we say only geometry that can be flat and exhibit the properties of our universe is infinite. So if we observe any significant curvature, it could have been closed like a sphere, 4D, 3D sphere, but we have not observed the curvature yet. Okay, so we all know that our universe is expanding. How do we know that? Doppler effect of galaxies that we have observed. So in 1929, Edwin Hubble observed that the galaxies, all the galaxies that he observed are moving away from us. All right. So he observed a law that the farther away the galaxy is the distance from Earth, and this is the receding velocity. So he observed a correlation that the farther away the galaxy is, the faster it is moving. And the slope of this best fit line, he named it, he did not call it as Hubble constant, but we call it as Hubble constant. So the relationship is velocity equals to h naught times the distance. Okay. Hubble constant is not actually a constant, it is a time dependent parameter. So he observed the value of h naught to be what it was at his time. When he measured it, it was something changes as the universe expands, and it was different in the past. So this is the graph he made. Hubble's constant, the rate of expansion is actually increasing, so universe is accelerating. But in the past, it was decreasing or remained constant for a bit of time. Okay, so around 380,000 years after the Big Bang, the universe was extremely hot. It was so hot that the nuclei and the electrons were not bound together. It was in the state of plasma. So the electrons and the nuclei were not bound together, they were uh, free to move. And plasma is opaque to any electromagnetic radiation. So the light cannot pass through a plasma. It scatters off the electrons and it remains trapped in a place. So all of the light in the universe was trapped inside a ball. But as the universe was expanding and hence was cooling down. So around 380,000 years after the Big Bang, it cooled down enough so that the electrons and the nuclei were bound, and hence the light was able to freely move through space. And we can observe this light that was emitted. It was Earth is at the center because we are observing it from here. So the light was emitted from everywhere, like these shells were there. I mean, these are hypothetical shells, they were not in reality. These are equidistant from Earth. So we can observe this light, and this is the oldest light we can observe using our satellites. So this is the map we got using WMAP satellite, and you can see the uh, blue and red and orange regions. They all have different temperatures, very slightly different. They are different to the order of 10 to the power minus 5 Kelvin. So the temperature of this was fairly in thermodynamic equilibrium, meaning every part of this sphere was equally, the temperature was equal, but it differed only slightly, around 10 to the power minus 5 Kelvin. Because we have our theory that universe was very hot and then it cooled down, and then there was a time when the photons were able to move freely. We had this model before we found the microwave. So since this fits, it is coming from all directions, it is not coming from a specific source, so we can say it was formed due to this. And it is extremely redshifted, meaning the temperature of this microwave is around 2.7 Kelvin, which is 2.7 degrees above the absolute zero, and its wavelength is 2 millimeter, which is very long for light. Okay, so Microwaves, I mean, there can be radio waves from pulsars, I think. Yes, it can. But the microwave will be a much higher frequency than this. This is very cold and very red shifted. We can isolate this frequency around this frequency and tell ki this is coming from the CMB. Almost no else, none of the other sources can emit this. This is very cold. This is coming from a black body that is at 2.7 Kelvin. None of the neutron stars can be this cold. So we can say that it is coming from CMB. Other thing is the Hubble tension. So scientists actually measured this Hubble constant. This was the constant between the distance and the velocities of galaxies. So scientists measured this constant using two different methods. One is from the CMB. They did some data analysis on the CMB to find what this constant must be, and the other was direct measurement. They looked around and they measured the receding velocities of galaxies around our neighborhood, and they measured another quantity. So actually, these two quantities are not in agreement. As you can see, one is 67 and other is 73. So this is known as the Hubble tension. This is one of the most important problems in cosmology right now. To resolve this tension, to tell why this Hubble constant, which is supposed to be equal from which is supposed to come out to be equal, is two different values. So whatever the resolution will be, we will learn something new about physics. Either our data analysis methods of CMB are wrong, or our models of gravity and evolution of our universe must be slightly different from what we assume. Okay. So the main force affecting the evolution of our universe is gravity, and we all know the best model we have for gravity right now was given by Einstein. It is general relativity. So understanding this equation, this is called the Einstein field equation, is very essential for doing cosmology and understanding what and learning about what happened to the evolution. So I will explain roughly what each term in this means. You don't have to know exactly what it means, just roughly what it means. So the left hand side of the equation is has three quantities, four. These four quantities appear in the left hand side. So these three quantities are related to the curvature. So we all know what Einstein did. Einstein found for gravity. It is that any mass creates a curvature in space-time fabric. We call it a fabric, and that creates the illusion of a force, which we call gravity. So this term captures whole of the geometry of space-time. Every curvature we can curvature at every point we can find out using this term. This is called the metric tensor. Uh, it is a 4 by 4 matrix you can write, because mu and nu can take values time x y z. So we have four coordinates: time x y z. So it can take total of 16 values. All of them are not independent. 10 of them are independent, and we can derive this quantity. These all these three quantities tell about the curvature of our universe, the geometry of our space time, and these two can be derived from this quantity. And the right hand side is given by, this is called the energy momentum tensor. It has every information you can have about the energy and mass content of our universe. So in Einstein's gravity, not only mass but energy densities can also create gravitational force. So this tensor has its component. We can write our mass distribution in terms of inside this. So our main goal for doing this general relativity is to find our geometry of our universe, finding what this should be given a mass distribution T mu nu. So generally, it is almost impossible to find what G mu nu will be given a arbitrary mass distribution. But for highly symmetric mass distributions, we can solve for G mu nu analytically using pen and paper. So the first solution was given by uh, Schwarzschild for a spherically symmetric, non-rotating, non-charged body, and it turned out to be solution for a black hole. And Schwarzschild gave that solution when he was in World War One. He was in the trenches doing mathematics. So So without these symmetries, like Schwarzschild found a solution for a spherically symmetric body which is non-rotating and non-charged. And we also found the solution for vacuum where there is no mass around. So without these symmetries, we cannot find the solutions explicitly for G mu nu. So we will see how we find this quantity for our entire universe and what symmetries our universe has, which allows us to find it explicitly. As we saw in our cosmic microwave background picture, it was almost entirely at thermodynamic equilibrium. Every point was at same temperature. No point was different from any other point. The differences were very minute. So in general, we say that our universe on very large scales, around a million megaparsec, I think, is homogeneous and isotropic. Homogeneous means no point in the universe is special. Every point is equivalent to any other, and isotropic means it looks the same in every direction. From every point you see our universe, you can point a telescope to any direction, any angle, and the average density of galaxies will be almost equal. So we say our universe is homogeneous and isotropic, and exploiting these symmetries, we can find the solution for G mu nu, which we wanted for our entire universe. So three people, Friedman, Robertson, and Walker, found this solution to be the metric of our universe. So if you don't understand what this is, it's fine. We will come back to it after I talk about what a metric is. Okay. So we can have any type of geometry, flat, curved, and we want to know how uh, distances between 2 points are related. So in flat geometry R3, we know the Pythagoras theorem. We can, if we have 2 points in our flat geometry, x1, y1, z1, x2, y2, z2. We know what the formula for distance should be in this. It is just So this is from Pythagoras theorem. This is this quantity. We can tell what the distance is. So our metric is a quantity that explains what this distance must be for a arbitrary for an arbitrary shape, like on a sphere. The distance between these 2 points would not be equal to this formula. It will be this distance which is given by this formula, and we want what the distance must be on the surface. I mean, if you cannot go through the sphere, what should be the distance between these 2 points? So it will be given by the metric of the sphere, which will be different from this. So we can write this equation. We relabel the coordinates y and z to be x2 and x3, and x as x1. So x1, x2, x3, these are three coordinates. These are x, y, and z. These are not exponents, these are just superscripts. So we can write this formula as So I have just used a summation sign and introduced this 3 by 3 matrix. This has I goes from 1 to 3, j goes from 1 to 3. So this is a matrix gamma 1 1, gamma 2 2, gamma 3 3, and we can write our distance formula in this way for any general shape. This is known as the metric. So the shape of the manifold or shape of the geometry we are talking about will be given by this matrix. So in our Euclidean case, this matrix will be just 1 1 1. If we diagonal 1 1 1, and everywhere else there is a 0. If we do this summation, it will come out to be delta x square plus delta y square plus delta z square, delta x1 square plus delta y1 square. And for simplicity, we will use the Einstein summation convention, which Einstein introduced, so he does not have to write these summation signs all the time. What summation convention is if we see a repeated index, in this case I and I is repeated 2 times and j is repeated 2 times. So we will automatically take a sum over these indices if there is a repeated index. So we can just write this formula, distance formula, like this. For our sphere, we know, you all know spherical polar coordinates. You know how to write a line element between them. This is the line element. ds square is dr square r square d theta square and r square sine square theta. So we can again write this distance ds square delta square. We can take these distances to be very small and replace the deltas with infinitesimal quantities. So ds square will be dxi dxj delta gamma ij. And in this case, the gamma will be the diagonal matrix with the prefactors for from dr square, d theta square, and d phi square. So that diagonal matrix is known as the metric of a sphere. So just like that, we found the metric of our whole universe using the isotropy and homogeneity of space-time, which we assumed. So this matrix which we see is equivalent to what we did for sphere and uh, flat geometry, because it is 4 by 4 matrix because there are 4 coordinates, time x y z instead of just x y z. So the only thing you have to know in this solution are 2 quantities, which is a and k. See, here is the speed of light. So what is a and k? So a is known as the scale factor of the universe. We know the universe is expanding, meaning its scale is changing with time. So we say a is the scale factor. So take a box at time equals to t1. Since that because of the expansion of the universe, this box will become bigger. Its side length was 1 1. Now it has side length 2. So we say that our scale factor has doubled. Scale factor went from being 1 to 2. So this scale factor captures everything we have to know about the expansion of the universe. And this k quantity, this should be k equals to greater than 1 and k less than 1. So this k tells us about the geometry of our universe. If k is greater than 1, it is a closed universe like a sphere. Sphere is closed, it is not infinite. K equals to 0 corresponds to our flat universe, which we have observed to be flat within experimental error. And k less than 1 corresponds to an open universe, like the shape of a hyperbola, a 2-dimensional or 3-dimensional hyperbola, which is like the Pringle shaped. It is bent. It is like the saddle of a horse. It is two hyperbolas like this. So these three quantities, this k quantity corresponds to the shape of our universe. Both of these quantities occur in this metric as a square and 1 minus kr square. So for rest of this talk, we will set k to be 0. because experimentally we have observed it to be 0. So using the metric which was derived and Einstein's field equation, we come up with these two equations. They are called the Friedman equations, and they are the most important equations for cosmology. We derive everything using these equations. So this is a differential equation in terms of the scale factor A, and rho and P are the energy densities and the pressure. So I talked about P mu. It looks something like rho P P P. So rho is the energy density which we are talking about, and P is the momentum densities. So if a particle is going in x direction, it will have certain momentum. In y, it will have something. Z, it will have something. Since our universe is isotropic, it is equivalent in all three directions. So all these three values must be equal. So this Friedman equation is in terms of A and its derivatives, and it relates the curvature K with the energy density rho. In the expansion of our universe. Okay. So since our universe is expanding, which means A dot, which is the rate of change of the scale factor, it is non-zero. If our universe was static, A dot would have been 0. And we have observed that our universe is also accelerating in expansion, meaning A double dot is positive. From this, the second equation, which says that A double dot upon A is proportional to minus P rho plus 3P. Since our universe is accelerating faster and faster, yes, I will come to that. We observe that this quantity A double dot is positive because our universe is accelerating, and right side of it is negative. So how can a universe expand if the right hand side is negative? It should be positive, which means this quantity rho plus 3p, for normal matter, rho and p both are positive. So any normal matter, like things we observe, electrons, protons, neutrons, they cannot cause the acceleration of the universe. From Newtonian gravity, we can say that if we have a clump of matter, it will always contract and collapse. So why is our universe expanding? And it is expanding at an accelerating pace, meaning the velocity, the galaxies which are far away are going away at higher and higher velocities at time as time passes. So we introduce a new kind of negative pressure. This energy density still cannot be negative. It always has to be positive. This pressure, we say that there is an exotic kind of energy which is known as dark energy. It causes a negative pressure and causes our universe's expansion. So for dark energy, for A double dot to be greater than 0, we should have P less than minus rho by 3. We can derive this relation from here. So no normal matter can cause this accelerated expansion. So we introduce a hypothetical quantity called dark energy. We do not know what dark energy is yet. So the search is still going on for the explanation. So so the Einstein equation I wrote had this lambda quantity in it. It is called the cosmological constant. So when we derive these Friedman equations, we set lambda to be 0. But if you derive the full Friedman equations considering lambda, it comes out to be this. If lambda is big enough, it can cause the right hand side to be positive. Understand that? So we call this lambda to be the dark energy factor. Okay. So the talk was on inflation. So I will tell about some problems in our old cosmological models that caused us to consider why we should take inflation into account. Inflation is it is exponential expansion of our universe right after the Big Bang. So first I will talk what was the problem with our old cosmological model. Then we will talk about how inflation solves it. Okay. So you are here on Earth. Since speed of light is constant, anything which is in a certain radius can affect you. It is called your it is called your particle horizon. Anything that can send light to you can affect you. Since speed of light is constant, the whole universe cannot affect you, cannot send you signals. You cannot observe the entire universe. So you can only observe your own particle horizon. So every particle has its own particle horizon, and it can only be affected by things inside the particle horizon. So when we saw our image of the CMB, it was something like this, and you are situated here, and every point was in thermal equilibrium. So there was a point here and point here. Uh, so this was suppose the radius of the universe when CMB was formed was r. So this distance is r by 2. This distance is r by 2. So any particle can only observe what is inside this r by 2 radius. So you can observe particles which are situated here. But these particles do not have contact with each other, since they also have their own particle horizons. And these two particles do not lie inside each other's particle horizon. But we observe that the temperature of each of those points are same. How do these two particles, which are not in causal contact, know that they have to be at same temperature? This is called the this is called the horizon problem. Why is the temperature of CMB so uniform when uh, every particle was not in contact with the whole universe at that time? So they cannot have same temperature. If what? But they have to start at the same temperature to lose heat at the same rate and ultimately be in thermodynamic equilibrium. How do you know that? Yeah. But in CMB space, when did they start at the same temperature? We do not know that they started at the Big Bang. We only know what happened after the Big Bang. The universe is very dense and very hot, so the particles can have arbitrary temperature. And when it expanded, they were not in causal contact, and still they had same temperature. Right now, right now the Hubble constant is around 70 kilometer per second per megaparsec. So, any galaxy that is 1 megaparsec away from us is receding at 70 kilometer per second. Double the distance, double the speed. It is a unit of 1 over time. So, kilometer and megaparsec has distance units of distance, and this whole thing is a unit of 1 over time. I mean, I don't know the physical interpretation of the unit of the Hubble's constant. It just comes from the relation V equals to HD. So this is meter per second, this is meter. So H has the units of. No, things cannot move through space at more than the speed of light. There is no restriction on the expansion of space. So the space can expand at any rate. So we have this relation. The velocity is directly velocity is equals to the Hubble's constant times the distance. If we put velocity to be the speed of light, we get a distance c over h. So anything that is at this distance from Earth or beyond this distance is moving at the speed of light or more than the speed of light away from us. So there is no restriction on the expansion of space. You cannot move through space at more than the speed of light. We also have another problem with our old cosmological model, which is called the flatness problem. As I said, we have observed the universe to be flat, approximately exactly flat. So the Hubble constant is defined to be A dot by A. We saw the Friedman equation to be this A dot by A squared. So we can replace this A dot by A with H. Okay, so this is what I have written here. So for this equation relates the curvature, the shape of our universe, the value k, with the energy density content rho. So if we fix a time t, the Hubble constant is fixed, Hubble parameter is fixed, and then if we increase or decrease the energy content in a rho, we can change the shape of the universe. So for a very specific value of rho, the shape of our universe will be flat, meaning k will be 0. So in this equation, if we set k to be 0, we get our critical density, we call it. It is the density of our universe which is needed for the universe to be flat. If our density is more than this, our universe will be spherical. If it is less than this, it will be hyperbolic. So at exactly this density, our universe will be flat. And we observe our universe to be flat. So if universe had infinite choices for setting the density of our universe, then why did it choose it to be exactly at the critical density? This seems like a very big problem. Now it is not exactly 0, but yes. But the thing is, uh, we observe this value to be approximately k approximately 0. Suppose k is okay. So I'll come back to it. So we define another quantity omega to be the density which is present at this moment in our universe divided by the critical density. So this equals to 1 corresponds to k equals to 0, right? So if this quantity rho is equal to the critical density, we will have a flat universe. So experimentally, we have observed this quantity to be approximately 0 equals to 0.01, and we can show using Friedman equations that this quantity omega inverse minus 1 must have been extremely this quantity is 10 to the power 60 times what it was when the universe began. So if it is 0.01 right now, it was approximately 10 to the power minus 62 when the universe began. So if we use this, we can take this to be 0. This is 0.62 decimal places. This is 0. This gives omega to be 1. So even if we observe our curvature to be slightly off from the 0 value, when the universe began, the density of a universe was exactly 1. So if it is not a problem right now, it was a problem when the universe began. Why universe chose the density of our universe to be at the critical density? Both of these problems can be solved if we introduce inflation. Okay, so first let me explain what inflation actually is. So we say our universe began as a very hot, this is only our observable universe. So there can be more stuff outside this. But I'm only drawing our observable universe. At the beginning, it was very dense, very small. Then we say that around the beginning, it expanded exponentially. So within the span of, this is the time axis and this is the uh, space axis. So within the matter of 10 to the power minus 32 seconds, the size of the universe multiplied by 10 to the power 20 orders. So this era is known as inflation. So this is marked by exponential increase in the size of our universe. So we will see how this thing, the exponential increase of the size, can solve both of the problems, the horizon problem and the flatness problem. So in the CMB, we saw that the two non-causally connected regions were at thermal equilibrium. So if we assume that inflation is correct, so we can rewind time and we can bring those two particles extremely close together because our universe began as that. And when they are extremely close together, they are in thermal contact, right? And they are in thermal contact, meaning they are in causal contact, meaning everything inside this region is at uniform temperature. And then after inflation happened, it expanded the universe exponentially and threw these opposite points outside their particle horizons. So they went from being in thermal contact to not being in thermal contact. So since they were earlier in thermal contact, the whole universe was in thermal equilibrium. When it expanded, it had no reason to go out of that. So using this exponential expansion, we can explain that why these two points are in thermal equilibrium when they are not in causal contact. Now for the flatness problem, we can write our Friedman equation in this form, that this is a constant. So uh, our universe was dominated by dark energy, a type of dark energy, since only that kind of energy can cause a expansion, accelerated expansion. So dark energy has a very peculiar property that its energy density does not change when the universe expands. So energy density of any normal matter will dilute as the universe expands. So its energy density will fall. But dark energy has this property that its energy density remains almost constant. And this quantity is a scale factor. It increased exponentially. So this whole quantity increased exponentially. For this thing to be constant, this must decrease exponentially, right? Since the multiplication is constant, if this becomes very large, this has to be very small. And if this is very small, it puts the quantity we wanted to be exactly equal to 1. So if we assume uh, this scale factor increased exponentially, it will also solve the flatness problem, as it will set the density of our universe to be around the critical density. So this is how inflation solves both of these problems. Okay. So how can this exponential expansion work? If universe was filled with matter, it will not happen. So we say that universe was filled with a special type of field at that time, which we call as inflaton field. That's not a typo. That is called inflaton field. Okay. So do you know what a field is?
Field in what the
Any field in physics? No, not field in physics, like electric field, magnetic field. What a field is? So field is a thing that attaches a quantity. It can be a scalar, a vector, a tensor, anything, to each point in space. Like we can have temperature field. It attaches a temperature to each point in space. We can have potential field, electric potential. It is also a scalar field. Electric magnetic fields are vector fields. So in the same way, we say that inflaton, which caused the exponential expansion of our universe, was a scalar field. It had specific value at each point in space. Okay. So our we had this quantity called the Lagrangian. We do not have to know what a Lagrangian is, but we can derive the quantity we wanted, the energy momentum tensor, from this Lagrangian. So if we take this as the Lagrangian, we get our energy momentum tensor, which if you remember was of the form energy density and then momentum density. So using that Lagrangian, we calculate this rho and p, the energy density and momentum density, to be like this. It looks like a kinetic and a potential term. This half pi dot square looks like half mv square, and then there is the potential which we had in our field. It had potential and kinetic energy. So remember, we said that the for a double dot to be greater than 0, p by rho should be less than minus 1 by 3. Using our Friedman equation, we can set a double dot to be 0, a double dot to be positive. So this gives this quantity. And now we see that this momentum, this p term, it has a minus sign. So if the potential is large enough, it can overpower the kinetic term half phi dot square, and this p quantity can become negative. So overall, this field can act as a repulsive field. So this can cause our inflation. So typically the problem, the current research in inflation is going on. It is to find what this shape of the potential should look like so it can match the conditions of our universe right now. So this is the main question, what the shape of the potential is like. But we know how it should look like approximately. This is the potential, this is the value. It should look something like this. So starting from here, this inflaton field has very much potential, but not much potential energy, which means this term P half phi dot square minus V is negative because potential is very much larger than the kinetic term. So when this is the case, our universe start accelerating, expanding. This is known as the phase of inflation. So if we assume a ball to be here, it will roll down this slope very slowly. This is known as slow roll inflation. When it is rolling down, it is gaining kinetic energy. So we can think of the kinetic energy of the ball as the kinetic energy of our field. So when it reaches here, approximately, it gains enough kinetic energy so that this term half phi dot square minus V becomes 0, which means it has gained enough kinetic energy so that it equals to the potential energy. And at this point, the inflation stops. And this ball rolls down and then it goes into this well. So at the beginning of inflation, our universe was empty. We assume that there were no particles right now. There was only this scalar field. So it is there is only scalar field and no other particles. So how do these particles come from? Where do these particles which we see around us come from? As we would see that when a ball goes into a well, it oscillates back and forth. And we say that during this oscillation, this field couples to the standard model fields. You know the standard model. We have our electron quarks. It couples to those fields and it dumps its energy into those fields, which causes the particles in that standard model fields to come out. You know the particles are excitations in the field. So if we have the inflaton field and it dumps its energy into the standard model fields, it will create standard model particles. So we call this as the hot Big Bang when the particles were created. And this is also known as reheating because the universe was cold and empty, and then this inflaton field created particles. So at the end of inflation and at the end of reheating, our universe is filled with standard model normal particles, and it is dense, it is hot, and it is still expanding. That much is clear? Okay. So we assume that our universe was homogeneous and isotropic, completely homogeneous and isotropic. But still, we see that the CMB is not completely homogeneous. It has very small deviations from the homogeneity and isotropy. So how can we explain that? There must have been an explanation for that. If universe was completely homogeneous, there cannot be any structure formation, because homogeneity means every particle is surrounded by the same density of particles everywhere. So the net force on each particle is zero. And for stars to form and galaxies to form, the matter should collapse at a point. So if the universe was completely homogeneous, there could not have been any structure formation. So we see that in the CMB, the universe is not completely homogeneous, and this temperature difference actually corresponds to extremely tiny differences in the densities that were present at that time, and these higher density regions collapsed into galaxies and stars, and this is what we observe today. We can map our current current structure of the universe to this CMB and see that the density corresponded to the galaxies being formed. So we need to explain why there are anisotropies, as we call them, in the CMB. This can also be explained using inflation. Okay. So I will come back to how that anisotropy can be explained. First, we will talk about some recent data that has come out. So in 2023, I think, in 2023, a team of researchers found a background gravitational wave, a gravitational wave background coming from all points in the universe. Just like CMB was light coming from all directions, they found a very faint gravitational wave signature coming from all points in the universe. So they found this using something called pulsar timing arrays. You all know what pulsar is? Pulsars are extremely fast moving neutron stars. The neutron stars are highly magnetic, and hence pulsars have these jets coming from the ends of them. So there is a fast rotating neutron star. This is its rotation axis, and its magnetic axis is not always aligned with the rotation axis. So the jets can come like this, and as the pulsar rotates, this jet sweeps a area like this, a double cone, and if Earth comes in the line of sight of this jet, we can observe a pulse in our telescopes. So these pulsars are extremely, uh, they have a very constant rate of rotation. So we observe pulse fairly consistently. These pulsars have approximately atomic clock level precision. So the pulses do not change over time very much. So what this pulsar timing array did, this nanograv team did, was they looked at millisecond pulsars, which are pulsars with rotation times which is less than 10 milliseconds. So the pulses come about 2 or 3 or 4 milliseconds, and they kept track of their these timings over the period of 15 years. So this is our Earth, and they observed 67 pulsars in their whole year, 15 years. So these pulsars are randomly here, and we are observing their pulses, which are very consistent. Yes. These coming pulsar, they are electromagnetic waves, right? So how do they disturb the gravitational waves? When electromagnetic waves are propelling in the background of space, so if space expands, the waves expand with them. The redshift. Yes. Okay. So there are these pulsars. We are observing these pulses from each of them. And if a very big gravitational wave passes through them, there the time between these pulses, which was very precise, will shift a bit. So using these shifts from all the 67 pulsars over the period of 15 years, they found a gravitational wave. They say that they have found a gravitational wave background. So when we found the gravitational wave from LIGO, its wavelength was on the order of kilometer, 1 kilometer, 3 kilometer, 4 kilometer. But these gravitational waves that they have found, they have wavelengths of order of light years. So they are light year long waves, and their frequency about on the order of nanohertz. So they have found light year long gravitational waves permeating the whole universe, coming to Earth from all directions. There is no one preferred direction, and we need to explain where these gravitational waves might have originated from. So this is like these are pulsars and around the Earth, and we are observing them. So there are two, or there are many possible explanations, but we will see two explanations. One of them is inflation, and the first one is the collision of supermassive black holes. So the foremost explanation that people give is that somewhere in our universe, two supermassive black holes must have collided, and that would have caused these long gravitational waves. So the gravitational waves we observed from LIGO were from collision of two stellar mass black holes. So this kilometer long gravitational waves are produced when two stellar mass black holes or two neutron stars collide, and we can observe them in LIGO. But when two supermassive black holes collide, they will form these big wavelength gravitational waves. But there is a problem with this collision of supermassive black holes, because supermassive black holes are present at the center of galaxies, and almost every galaxy has a supermassive black hole at its center. And when these galaxies collide, people say that this supermassive black hole will rotate each other and eventually collide. But the problem is, when two galaxies collide, these supermassive black holes come come near each other by revolving around each other, and losing their energy to other matter surrounding the galaxy to about 1 parsec. You know what a parsec is? It's about 3 point something light years. So they come near each other to about 1 parsec. They lose their energy to surrounding matter, and they come near each other. But in the process of coming near each other, they create an empty space around them. So there is no more matter to lose energy to. And now when we calculate the loss of energy, so they are revolving around each other. So why will they come close and collide? They have to lose energy somehow, so that they come close and close and close together. So the only process they have of losing energy is gravitational waves. There is no other process. They are Hawking radiation is extremely light. I mean, it is not very energetic. So I said the temperature of CMB is 2.7 Kelvin. And if we calculate the temperature of Hawking radiation coming out of these supermassive black holes, it will come out to be on the order of 10 to the power minus 5, minus 6 Kelvin. So instead of losing energy to Hawking radiation, they are actually eating up the CMB and growing. So Hawking radiation is extremely faint and extremely slow for these to lose energy. So when CMB will lose enough energy to be lower than the Hawking radiation, then the Hawking radiation will start to take over and evaporate these black holes. But right now we do not have any other mechanism. And if we calculate how much time it will take for two supermassive black holes, which are 1 parsec apart, to come together, it comes out to be more than the age of the universe. So we can say that no two supermassive black holes have ever collided since the universe began. So this cannot be a possible explanation. There can be more ways in which it loses energy, but right now we do not know about them. And since this gravitational wave is coming from all directions, so if two supermassive black holes must have collided, so it should have a preferred direction where they have collided, and that gravitational wave should come from there. But it is coming from all directions. So we see how inflation can solve this problem. So we say that the universe began before inflation. It was microscope. It was at the size of atoms. It was atomically small. So at this size, there are quantum fluctuations. Quantum mechanics will take over, and there will be quantum fluctuations. And these quantum fluctuations, which are extremely tiny, they can cause the density, which was isotropic, to be perturbed a little bit away from the isotropy. So these small perturbations in energy density, using the Einstein equation, this energy density will in turn cause the small perturbation in our geometry of space-time, and this small perturbation in our geometry can be thought of as gravitational wave. So when the universe expands, these gravitational waves will fill all of the universe, and it will not have any preferred direction, and it will be random because these perturbations, quantum fluctuations, are also random. So this is what we observe, a random gravitational wave background coming from all directions. It can be explained using inflation because the universe was very small and we had quantum fluctuations, and they can cause the formation of these gravitational waves. But the pulsar timing array has detected. We can find parameters of our inflationary theory to fit this energy density which we have found, and we can say that inflation could have made this if inflation is correct. Another thing you could have asked was, if universe was so dense in the beginning, why did it not collapse into a black hole?
So, the universe and one was
Or since universe was isotropic, there was net zero force on every particle and it cannot collapse. But now we see that isotropy is broken. It is not completely isotropic. So there were regions of higher density and lower density in the initial universe. And they could have collapsed if the density, higher density regions, the density was above some specific threshold, they could have collapsed into black holes. And these black holes would have been extremely small because the universe was extremely small. And these black holes, if the inflationary model is correct, it should form what we call primordial black holes. So we have till now seen two kinds of black holes. The supermassive black holes, we do not know how they are formed, but we know that they exist as the center of every galaxy. And then stellar mass black holes, which form from the collapse of stars. So these supermassive black holes are very massive, and the stellar mass black holes have their mass on the order of the mass of stars. So 10 mass solar mass, 100 solar mass, something like that. But if a black hole is detected below this mass range, it could not have been formed from the collapse of a star because of Chandrasekhar limit and all that. So if we detect a black hole which is below the mass, which is below the stellar mass black holes, it must have formed due to some other process, and inflation is one of the processes that can explain that. So we say that there was a field in inflation and all that. This is just a theory. So we do not have any confirmation about it. Most cosmologists think that this should be correct, but there are very many people who oppose this theory because they say that inflation has too many free parameters and it can be used to fit any data. So these are valid criticisms of a theory, but we do not have a better theory as of yet. So we say that this is what it should be. What should have happened was inflation. This is what we say, but there can be other explanation. It is not a proven fact. So that is all. Thanks a lot.